This video is going to show you how to calculate torque using force and distance, kind of an equilibrium problem for statics. So what I have on the screen is I've got a beam, and it's the brown stick, and I can see where the center of gravity, or also called the center of mass on the surface of the Earth, although we're going to talk about the center of gravity because we're talking about forces. So that's located right in the middle of the beam, because the beam is a uniform beam. So whenever you're doing a word problem and you see the word uniform beam, or the phrase uniform beam, that means the weight of the beam acts right in the middle of it. And you can see I've got W1 and W2, and then I've got the string holding everything up, and I've got these distances located on my free body diagram, or on my image of the problem. Now what I'm going to draw is an extended free body diagram. So for the extended free body diagram, you see I've got my line, that's why it's extended free body. And now I'll put the forces and any distances that I have up there on the diagram above on my extended free body diagram. So you can see the weight of the beam is right at the center of gravity of the beam, right in the middle of it because it's uniform. And then I've got W2, so everything's all set up. Now what I'm going to do is get rid of the diagram and focus on the extended free body diagram, because the extended free body diagram is what I would put on my paper. I need a pivot point, someplace, or a fulcrum, someplace where all the force is going to cause my extended body to rotate. I'm going to choose the center of gravity. So that's where that X is. That's going to be what's called the pivot point. The fulcrum, sometimes also called the axis of rotation. So lots of words to describe this point. They're all fine. So now I know that torque, that's the Greek letter tau, is equal to force and distance that are perpendicular to each other. So to help me see that, what I'm going to do is I'm going to take my vector for W2 and I'm going to draw it longer. And then I'm going to draw a line between the pivot point and this blue line that is perpendicular, that is, they're 90 degrees from each other. So there we go, 90 degrees from each other. That means that torque is the distance of the green line times the value for W2. In other words, torque is equal to W2 times 1 meter, because that's the distance from the pivot point that I chose and the line. So W2 is all it is, because W2 times 1 is W2. Newton meters. So the torque is measured in Newton meters. Not a special unit, just a Newton meter. Alright, now I've got to figure out if this thing is positive or negative. So to figure out if it's positive or negative, what I'm going to do is use what I call the pencil test. So I've got a pencil on the screen, and now this is really easy. In fact, I'm going to get my dog to help me. Sophie. Here it is. This is my dog, Sophie. So Sophie's going to help me out with this. Sophie, what I want you to do is I want you to put one paw on the pivot point. Nice. Now take the other paw and put it where W2 acts. Excellent. Okay, move the pencil in the direction that the force of W2 acts. Nice job. So there we go. Now I can see how my extended free body diagram will rotate using my pencil test. So it's going to rotate in this clockwise direction. And I know that everything that rotates in this clockwise direction is a negative torque. So that means I got to put a negative sign in front of my answer for W2 Newton meters. So there it is on the screen. So now that's a negative torque. All right, let's try another force. Let's try W1. Because W1 and W2 both point down, but I want to show you that I'm not going to get the same answer. So on W1, what I'm going to do is I'm going to, again, take my vector and I'm going to draw a long line just to make it easy to visualize. And I'll draw a line between the pivot point and this blue line that are perpendicular to each other. So there's the green line, 90 degrees, perpendicular to it. Great, I'm all set. So torque is the length of the green line, which is 2 meters, times whatever value there is for W1. So W1 times 2. So there's the torque, 2 W1 Newton meters. Now I need to figure out whether or not it's positive or negative. So I'll do the pencil test again. And I'll get my dog Sophie to help me out one more time. Alright, Sophie. Put your paw on the pivot point. Now take the other paw, put it where the weight is acting, and move the pencil in the direction of the force. Nice. So of course you wouldn't use your paws, you would use your fingers. But, you know, Sophie's the dog. Excellent. So we're all set. So this is going to cause a rotation in the counterclockwise direction, and we define that as a positive torque. So that's a positive torque. That means that my 2 W1 Newton meters is going to stay the way it is as a positive value. So let's keep going. One thing to point out here, though, is that W2 and W1 both point downwards, and yet I got two different signs for the torques, one positive, one negative. Because the signs don't depend upon the direction of the force, the signs depend upon the direction of the pencil rotating when I do my little pencil test. When it's rotating in a clockwise direction, it's a negative torque, and a counterclockwise, it's a positive torque. So let's try it with one more force. Let's look with the tension on here. So again, I'm going to take the direction the tension acts, and I'm going to draw a long line. And now draw a line between the pivot point and this blue one that are 90 degrees to each other. So there they are, perpendicular to each other. So the torque is going to be 1 meter times whatever the value is for the tension. So T times 1 meter, or just T Newton meters. Now I've got to figure out the sign. Again, pencil test, and my dog Sophie. Alright, so Soph, put one paw on the pivot point. Now take the other paw and put it where the tension is applied to the extended free body diagram, and move the pencil in the direction of the tension. Nice. There we go. So I can see that this rotation is in a clockwise direction because I saw how the pencil rotated. That's going to be a negative rotation by our definition. So this torque will be a negative torque. So I'll put a negative sign in front of it. So negative T Newton meters. Excellent. Ooh, one last force, I almost forgot. The weight of the beam itself. So if I draw a line, extend the vector, I can see it goes right through the pivot point. Well, if it goes right through the pivot point, there's no moment arm. If there's no moment arm, then force times 0 is equal to 0. So any force that points towards my pivot point or from my pivot point does not exert a torque because the moment arm is 0.